All right. Welcome. Covering section 3.3 today. Two big ideas. 5 letters. Cpctc. What does that mean? How can I use that? What kind of tool is that? Very popular to use in our problems. And then some shapes which are not going to be triangles are going to show up, and you need to know how to use them and talk about them, and these things we call actually circles. Okay? Excuse me. Let's start with the 5 letters. So, C, P, C, T, C. That's where they come from. Corresponding parts of congruent triangles are congruent. So if we can show 2 triangles are congruent, yeah? Is congruent to this triangle, right? And I know that these 2 triangles are congruent. Then I can take triangle A and triangle F, and I can say, oh, those 2 triangles have to be congruent because number 1, they're corresponding, right? And number 2, those 2 triangles are congruent. So all the corresponding parts have to be congruent. Now again, I could take the side as well. So here's a little proof that we're going to go through. Ignore the circles in the background. I'm not too sure why they're there. And we have given to us that SM and PM, so we're going to mark it up. And we know that this angle and this angle, also SMW, PMW, are congruent. We are trying to prove or show that these 2 pieces here are congruent. Our strategy, I think in general in these types of problems is, well, since we can't show that this is a bisector point, right, which would be kind of nice, but we don't have that information, we could say that, oh, show this triangle is congruent to this triangle. Once you know that, then I can use my little 5 letters, CPCTC, to show that. Okay? All right, how do I show those 2 triangles are the same? Well, that was been the lesson, the last lesson, and we have these acronyms, SAS, SSS, and ASA. And the trick is to figure out which one of those is going to be useful here, right? Hopefully you can see that side, side, side is not going to be useful to show the triangles. Number 1, they give us an angle. Number 2, those sides are the sides we're after, so I don't know that they're congruent. Second of all, we're going to cross off angle, side, angle, because I don't know anything about these 2 angles or these 2 angles here. Okay? All right. That leaves us with side, angle, side. So notice here we have the side and the angle, and then the side would naturally be that side. And that side is a shared side with the other triangle. So voila, as the French say, that middle segment, MW, is congruent to MW. And again, we call that the reflexive. Book calls it property. I say theorem, because we're talking about segments and not side lengths, right? And I suppose we should put given up here for number 1. All right. I like to put, by the way, after each piece what it is. So that's what the S and the A stand for, side and an angle. Okay? Helps me figure out what I need. Now I've got the side, boom. I can now say triangle, sorry, SMW. I was apologizing for the boom. Congruent to triangle PMW. And that would be SAS postulate. All right. Number 4, now we can finally, conclude. Because the 2 triangles are congruent, every side And every angle that corresponds to each other must be congruent. So we say Cpctc. All right. Now, for the things which are not triangles, we call them circles. They have a fixed point. That fixed point is the center, and it's typically labeled with 2 coordinates, which are the x and the y coordinates, so to speak. Yeah? Then we have a fixed radius, which is half the diameter. And we usually use the letter r to denote that number, the radius. And there's 2 formulas, area, right? What is the stuff inside the circle? How much stuff is there in there? How do we calculate that? You take pi times the radius times the radius. And most kids say, oh, pi r squared. Circumference. Circumference is just the distance around a circle. Okay, we call that, we label it with the c, and then we say pi again, magical number that it is, times 2 times r. Or, most books will rearrange that and say 2 pi r. But then some kids say, well, r times 2 is diameter, so why not just use pi times diameter? I like this to be the reference because it shows you the similarities between the two. And there's some other things coming down the pike that you'll see why that's a good way to think about it. All right, let's go to an equation. This is not in the book, at least not in the front of the book. It's towards the back of the book, actually. And before I show you a new tool, a digital tool, I need to reference something from your past. Do you remember when you talked about, maybe I should draw the triangle in that reference point, right triangles in the past? And somebody said, oh, if you know this side and you know that side, then you can find that side. And they called it the Pythagorean Theorem, and they said a squared plus b squared is c squared. Well, lo and behold, that's the type of equation that we use to write algebra equations for circles. So if I take an x coordinate and a y coordinate and I square that, right, set it equal to the radius squared, that generates the equation of the circle. Now that doesn't intuitively make sense. Why is that the case? And it may not for a while, but let me show you, kind of convince you that it does without taking a long time and building tables and spending another 40 minutes of our life. You go to GeoGebra.com, pause the video, let that load. I'm going to go to the app. Okay. Here we go. And let me delete, and let me change this. Okay, so here we go. GeoGebra opens up usually like this. It's a blank canvas. You have other options under that menu, but you typically have some tools you can pick, and you can look at the results. I'm going to start with the tools. We have a move tool, a point tool, a segment, line, polygon, and circle. Okay. Again, you grab a tool, bam, and all I'm doing is clicking on the screen, creates points. And you could do that with a line or a segment. Oop. Say we took a segment and we went okay?
Hey.
Hey.
So
no.
I got the test generator and I made my first quiz.
Beautiful.
When you have time, would you help me export it into Schoology?
I'll be right over.
No problem.
Okay. So here goes the circle. Sorry about that. I pick a point, I pick another point, and notice now I can grab, I'm going to take my move tool, I can grab my center, and I can swing my center wherever I want it. I can grab the point C and move it to anywhere I want. Yeah? Or I can grab the circle itself and move it about. So that's how we can create a circle and visualize it nicely in an app. But notice, I'm now going to show you the equation by turning on my grid and turning on my axis. So this gives us a reference point now to talk about the algebra hiding behind that. And to look at that equation, I'm going to do a couple things. First of all, I'm going to move the circle on the center. It's going to make it a little bit simpler. I'm going to move point C up to A. Up to 4. Okay. Now we hit that equation calculator thing at the top. And notice right there on the page, it says C, circle BC, and then it says x squared plus y squared is 16. So notice if I move the letter C down, it dynamically changes to 9 because my radius is now 3. Or I could move it down to on the x-axis, and you can see it's 4, right? One last thing I want to show you before I go, and that is if I move the center, notice my equation starts to go a little crazy too. Now I'm going to pause there for a moment and put the center at 1, 2. Yeah? And notice 1, 2 shows up in the equation. Now my radius is no longer 3. The radius has changed. It's now the square root of 8. Because remember, some number squared is 8. And we'll talk more about how that works in the future, but I just wanted to show that to you so you could have a reference of what's going on with circles on grids. Back to our notes. So there's the general circle again. X squared plus y squared is r squared is the equation of a circle with a center of 0, 0 and a radius of r. Okay? We'll put 0, 0 there as the center, right? And r is the radius. One more thing, one more tool, and this is the theorem. All radiuses is not the proper word for pluralizing radius, so we say radii. So all radii from the congruent circle are congruent, right? So whether you draw one circle or whether you draw 2 circles that are congruent, doesn't matter where you pick the radius, it has to be congruent to all the other radiuses. And if I have another circle over here that is congruent to that circle, then it will have the same radius. All right? So here we go. A theorem that covers just about all the waterfront. Do you see a circle? Do you see a radius? Well, guess what? We're going to use that theorem if you see that radius and you see that theorem. Now we do that right at the end of the problem. Let's first of all see what else is in here. We've got a circle, and we have 2 sets of angles that are complementary. So let's mark those angles that are complementary. So angle T is up here. Angle MOT is right here. So those 2 angles add up to 90. Okay. Angle S is here. And angle POS is here. And those angles are complementary. All right? One thing we need to note here before we move on is that there is an idea that we had in the last section of chapter 2, that those 2 angles that are like centered at the circle O, center of circle O, they're called vertical angles, and those angles have to be congruent. All right, so angle MOT has to be congruent to angle, I guess you could go POS or ROS, wouldn't matter how you name that, okay? P is starting from there and R is starting from there, and because those 2 angles are vertical angles, we can now mark them as congruent. And I suppose we should put a justification over here, VAT. All right? Now, if those 2 angles, which are complementary to their corresponding ones in the problem, then the corresponding or the complementary ones have to be angle 2, are congruent as well. So angle S and T, because they are complementary to 2 angles that are the same, congruent at least, then they would need to be congruent as well. So, complementary of congruent angles theorem. All right. Now notice we have 2 angles set up congruent to two angles. And if you think about like what type of triangles, how do I show, damn, sorry about that. How do I show those two triangles are congruent? Well, again, it's those three-letter acronyms, and hopefully you're not going to try side, 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 or side, angle, side. You're going to try angle, side, angle this time. Whoops. And we already have the angle here, and these angles congruent. All we need is the side in between. Oh, those were the radius that we had initially. So this line 4 could actually have been up here, right? Except you don't really know why you're needing it initially. So OT and OS are congruent. And we don't name that theorem ever. We typically just write down all radii are congruent. And what that means is that not all radii are congruent, but all radii in a particular circle or all radii in congruent circles are congruent. All right, 5. Now we know that those two triangles are congruent because we have an angle, a side, and an angle. So I'm going to now name that other triangle MOT, POS. Got to name it correctly. And we have the angle, side, angle postulate. And because we have the two triangles, now all the sides and angles are corresponding are congruent as well. So MO and PO are congruent by Cpctc. So this was a kind of a comprehensive problem that it covers a lot of different concepts that we've already studied. Okay?